Hello and welcome to your first lecture video for Statistical Methods 2. In this video, we're going to be talking about mathematical notation, specifically the idea of using subscripts and summation notation and what I'm calling indexing functions. So I want you to think about this topic as learning a new language. So the way we communicate statistical models, at least I think an effective way to communicate statistical models, is to write them down with equations and formulas. The purpose of this is to have a clear way, an unambiguous way to communicate the statistical model that you've chosen for your analysis, which we'll talk about more, characterizes what sort of assumptions you're making in the analysis. So if you're not someone that's used to writing things down formally in mathematical notation, this is going to be a little bit unfamiliar at first. But I want you to think of this like you're learning a new language. And the point of learning a language is to make sure you can communicate effectively with other people who are speaking that language. All right, so let's jump into this. So imagine we have a data set that looks like this. Here there are 5 observations labeled 1, 2, 3, 4, 5. And associated with each observation is a time. So this is, I just made up some times here. Think of these are marathon times in minutes. So the first observation 1, which is associated with some runner at some race, did 165.3 minutes in the marathon. All right, so if we want to refer to the data in this table, it's helpful to have some sort of notation. So here I'm writing, let I be an integer between 1 and 5. So I can be 1 or 2 or 3 or 4 or 5. And y subscript I, so y with a little I next to it, is the time associated with observation I. So if you were to label these columns, you could label them, the first one I, and the second one y sub I. So in this case, y sub 1 is the time associated with the first observation. And if you look up in that table, that's 165.3. Y sub 2 is the time associated with the second observation, and that's 158.8. So you could do this for each of these 5 observations. So one of the things we'll be doing a lot in this class is working with summations. So you probably heard of the sum of squares criterion. That's a sum, it's a summation. And what you don't want to do is have to write out the sum of each individual term like we have on the right side here. It's really helpful to have a concise notation for writing out things like this. And the concise notation is this thing on the left here. So if we want to add up all the marathon times, y1 plus y2 plus y3 plus y4 plus y5, we can use this summation notation. So the way this works is you put this big Greek letter here. This is the Greek letter sigma. Underneath it, you define what's called the indexing variable. So here I'm going to use I for the indexing variable. We define where we want it to start beneath the sigma symbol. So we're going to start with I equal to 1. And then above the sigma, you write where you want it to end. And then it's assumed that you're going to add up the thing that's to the right of the sigma for all values of I from 1 to 5 inclusive. So 1, 2, 3, 4, and 5. So what this means here is we're going to add up yi for I equals 1 to 5. And that means exactly what's on the right side of the equal sign. So we're going to get some practice with this in just a second. First point I want to make is that the choice of the variable for the indexing variable is somewhat arbitrary. Of course, you have to be consistent, but I could have just as easily chosen j. So sum j equals 1 to 5 y sub j is the same exact thing as sum I equals 1 to 5 y sub I. So what I mean by being consistent is that if you use j to define the indexing variable, you better use j in the variable that appears to the right of the sum. So it would not make sense to say sum j equals 1 to 5 y sub I, for example. All right, let's get some practice with this. So I've written out 5 different summations. And what I want you to do, and we'll try to do this throughout these videos, is to pause the video, take out a sheet of paper, and then just like we have up here, take this summation and write out what goes on the right side. So here we have sum I equals 1 to 5 of I itself. What I want you to do is to the right of the equal sign, write out all of the terms that appear in the sums. You don't necessarily have to evaluate what the answer is, but just write them all out and do that for each of these 5 examples here. So you can go ahead and pause the video now, get out a sheet of paper, and try that yourself. All right, let's look at the answers for these examples. So the first one is sum I equals 1 to 5 of I itself. So what we do is we start at I equals 1, and we write down 1. Then we move on to I equals 2, do plus 2. Then I equals 3 plus 3. I equals 4 is plus 4. And I equals 5, which is the last one indicated by the thing on top of the summation sign, is 5. Okay, this one's very similar. The only thing that's different is we start at minus 1 and we go up to 4. So you get minus 1. Next one is plus 0, plus 1, plus 2, plus 3, plus 4. All right, this one is slightly tricky because inside of the thing on the right, inside of these parentheses, I have not just I, but I'm subtracting 2 from I. So for I equals 1, so this is going to be 1 minus 2 is minus 1. For I equals 2, you're going to get 2 minus 2 is 0. For I equals 3, it's 3 minus 2 is 1. I equals 4, it's 4 minus 2 is 2. I equals 5, it's 5 minus 2 is 3. And I equals 6, which is the last one, and 6 minus 2 is 4. So you'll notice that this thing here is a different summation on the left side, but it turns out that you're adding up exactly the same numbers on the right side. So one thing to remember is in mathematical notation, there's often more than one way to write out the equivalent thing. I'd argue that this one up here is a little bit simpler, but you might prefer to always start your summations at 1 and go up to some number. So in that case, you might prefer to do the second one. All right. The next one is I equals 1 to 5 I squared. So it's going to be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. If you wanted to write each of those out, you would get this. And then the last one is slightly tricky. It's minus 1 to the I power, starting at 0 and going up to 3. So minus 1 to the 0 power is 1. Minus 1 to the 1 power is minus 1. Minus 1 squared is minus 1 times minus 1 is 1. Minus 1 cubed is minus 1 times minus 1 times minus 1, which is minus 1. So this one evaluates. Okay, just a brief aside. One of the summations looked like this. Sum I equals 1 to n. Here we did 5 of I itself. So if you were to write that out, one way of doing is to do the first few to see the pattern and then do a dot, 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 which is not really mathematically rigorous, but usually you can see the pattern and understand what that means. And then write out the last few. So this is unrelated to what we're doing in the class, but I just thought this was interesting. There's actually a formula for what this summation is, and let me show you how this works. So if n is even, you're going to have an even number of terms in this sum. So one way to evaluate this is to start grouping the terms up into pairs and then adding them up together. And the trick for this one is to carefully pick what the pairs are. So if you add up the first one and the last one, you get 1 plus n. And then you add up the second one and the second to last one, you get 2 plus n minus 1. And the third to the last, you get 3 plus n minus 2. So if you look at each of these, and then you would keep going until you get down to the two middle ones. If you look at each of these, they're all equal to n minus 1. So 1 plus n is n plus 1. 1 plus n is n plus 1. 2 plus n minus 1, you get n plus 2 minus 1 is 1. And then same thing here, n plus 3 minus 2 is n plus 1. And then you count up the number of these, you get n minus 1. Since you had n terms and you put them into pairs, you get n over 2 pairs. So the total sum is just n plus 1 times the number of them, which is n over 2. So this is a formula for what this summation is when n is an even number. Now we have to look at the odd case. So what we do for the odd case is we leave the last one alone. So just put this aside, the plus n, for a minute. And then do the pair thing for 1 and n minus 1, 2 and n minus 2, 3 and n minus 3. So if you do that, you get 1 plus n minus 1 is n, 2 plus n minus 2 is n, 3 plus n minus 3 is n. So you're going to get n for every single one of these pairs. And then you have to count up the number of pairs. In this case, you left this last one alone and you just work with the first n minus 1 and then paired them up. And so there are n minus 1 divided by 2 pairs. That's why I say n minus 1 over 2 times. And then you can't forget about this last one here. So this becomes n, which is the value that we're summing up, n minus 1 over 2 times, plus n. And then if you do some algebra here, factor out, and basically you have to factor out n, you get 1 plus n minus 1 over 2, all times n. And then if you do a little bit more algebra, it turns out you get the same exact formula, n plus n minus 1 over 2 when n is odd, as you get when n is even. So this is just an aside unrelated to the course, but this is a sort of a clever example of how to add up the first n integers. Okay, so the next practice session is what I want you to do is to do the opposite of what you did before. I'm going to give you the written out sum with each individual term, and what I want you to produce is the thing that was on the left side before. I want you to write it out in summation notation. So, for example, if I gave you 1 plus 2 plus 3 plus 4 plus 5, I want you to write out what that is in summation notation for these 5 examples. So you can go ahead and pause the video, get out a sheet of paper, and write those out. All right, here are the solutions. I've just rewritten them on the left side here. So the first one was 1 plus a half plus a third plus a fourth plus a fifth. So if you notice the pattern here, each term is 1 divided by each successive integer, 1, 2, 3, 4, and 5. So the summation notation on the right side is sum I equals 1 to 5 of 1 over I. This has a special name. This is called the harmonic series. This one here, we have 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16. Now, if you're clever with exponents, what you'll recognize is that this is 1 over 2 to the 1 power. This is 1 over 2 to the 2 power, 2 squared. This is 1 over 2 to the 3rd power. This is 1 over 2 to the 4th power, which is what I've written here. So you can see that the indexing variable should be the exponent. So this is 2 to the 1, to the 2, to the 3, to the 4. And you can write out the summation exactly like this. This, by the way, is called a geometric series. This one is exactly the same as adding up 1, 2, 3, 4, and 5. I've just put it in the reverse order. Technically, you could write I equals 5 to 1. If you wrote that, people would understand that you're supposed to count down from 5, 4, 3, 2, 1. But if you just use the property that you can, if you're adding up a bunch of numbers, you can add them up in any order you want. You could start at 1 as well and say this is I equals 1 to 5 summation of I. All right, this one's a little bit tricky because it doesn't go from, it's not immediately obvious that this is like this corresponds to I equals 1, this is I equals 2, this is I equals 3. But this is just 2 times 1. This is just 2 times 2. This is 2 times 3, 2 times 4, 2 times 5, 2 times 6. So one way of writing out this sum is to say I equals 1 to 6 of 2i. Now, one thing we'll learn later in the semester, or we can just do it right now, is that we could rewrite this sum by factoring out the 2. You could put the 2 outside of the summation and do 2 times summation I equals 1 to 6 of I. That's the same thing as factoring out a 2 from each of these terms and writing 2 parentheses 1 plus 2 plus 3 plus 4 plus 5 plus 6, close parentheses. All right, this one is very similar, but instead of adding up the actual number 2i, we're adding up the 2ith subscript for y. So if we had 8 marathon times and we wanted to add up the marathon times corresponding to the even indices, we would write it in summation notation like this. So I equals 1 to 4, y sub 2i. So I equals 1, you get 2. I equals 1, you get y sub 2. I equals 2, you get y sub 4. I equals 3, you get y sub 6. And I equals 4, you get y sub 8. Okay, now let's make this slightly more complicated. So we have a new data set here. It's still going to be 6 marathon times, but in addition to just labeling the observation 1, 2, 3, 4, 5, 6, we're going to provide some additional data on who produced this marathon time and at which race they produced it. So if you look at this data, you'll see that the first 3 observations correspond to marathon times from the first runner in our data set. The second 3 correspond to marathon times from the second runner in our data set. And then the third column tells us, at least it's a label that tells us which race the marathon was run at. So of course the runner, this is just a label as well. This corresponds to a human being. Likewise, the race number corresponds to a specific race. So the first one might be Boston Marathon, the second one Chicago Marathon, and the third one London Marathon, for example. So in this data set, the first observation is a marathon time from runner 1 at race 1. And then the second one is runner 1 at race 2. The third one is runner 1 at race 3. And then the next 3 are from a different runner at the same 3 races. All right, now I want to talk about here is what notation we're going to use for the marathon times, which we denoted as y before, specifically y sub I before. And there's more than one way of doing this, so I'm going to give you 2 ways of doing this. But what I want you to keep in mind is that neither is right. They're both correct. But what you really need to do, the important thing is that you're consistent in what notation you use and that you define it clearly for anyone who's going to be reading the paper. So the first way of doing it, which I'll call single index notation, we'll come back to this later in the semester, is I'm just going to label them Y1 through Y6. So this is unambiguous because I can look in the data set. If I refer to Y sub 2, I look in the data set. That just means the time corresponding to the second observation in the data set. So if I were writing this up in a sentence, I would say Y sub I is the time associated with the ith observation in the data set. So this one is perfectly fine as long as you say what Y sub 3 means, for example. Now this next one is not okay, and you should see why. So what this one is saying is that Y sub I is the time for race I. Now this one is not okay because here you would label it Y1, Y2, Y3, race 1, race 2, race 3, and then you would have to reuse the symbol Y1, Y2, and Y3. So now if you were to refer to Y sub 2 somewhere later in the paper as the time for race 2, now it's ambiguous which specific observation this refers to. It could refer to this one, 176.7, or it could refer to this one, 163.1. So this may seem obvious, but I just saw a recent paper that makes a mistake that's similar to this, which it's ambiguous over which observation it's referring to, and this caused me to not really understand what they were doing in the paper. Now, another way of doing it that's correct, maybe correct's not the right word, that's unambiguous, is to use two subscripts. So here what I'm saying is Y sub ij is the time of runner I in race J. Now the reason this is unambiguous is that each runner will have only one time for each race. I suppose if you did this over multiple years, you would need another subscript to determine the year. But in this data set, we just have one observation for each runner in each race. So this one also is unambiguous. And so, for example, Y11 corresponds to the time for runner 1 in race 1, and Y23 corresponds to the time for runner 2 in race 3, which is the last row in the data set. So you have to be careful with this. Sometimes it's easy to flip the subscripts and talk about YJI when you really mean YIJ. Another kind of weird thing is that it's maybe sometimes not easy to distinguish between Y13 and Y13. So if it's ambiguous, you can put a comma between the 1 and the 3. But the main thing to remember is that you just always define what the notation is. It's good to have a sentence, something like this: Yij equals the time of runner I in race J. Or up here you would write Yi is the time for the ith observation in the data set. So either one you pick, the most important thing is that you just define what the subscripts mean so there's no ambiguity. Again, what this is all about is clearly and unambiguously communicating to the reader what you're doing in the analysis and what you're talking about when you refer to specific observations. Okay, the next thing that we're going to be using quite a bit this semester are what I'm calling indexing functions. I'm not sure that this is a common terminology for this sort of notation, but that's what we'll call it in this class. So what this means is I'm going to define a function. So this is a function that I'm calling j, whose input is an index I. That's why it's called an indexing. That's why I'm calling it an indexing function. So if I define j of I to be the runner who produced observation I, this allows me to define everything in terms of the I, the row of the data set, but also refer to the runner who produced that observation. So if we look at, let me see if I can get this on the same screen. Well, almost. So just a reminder, this is, let me make this smaller so we can see it. Okay. So J of 1 is the runner who produced the first observation. So the first observation comes from runner 1. So J of 1 is 1. J of 2 is the runner who produced the second observation. So here's the second observation. This is the runner that produced it. So this is also 1. The third observation also came from runner 1. J of 4, so we look at the fourth observation. This was produced by runner 2. So J of 4 is 2, and so is 5 and 6. Likewise, you can define K of I to be the race at which the ith observation was run. That's kind of a tough sentence to say, but all we mean is that if I look at the ith observation, which race did it come from? So what I want you to do is pause and just write out what each of these are. So these are all going to be either 1 or 2 because there's only 2 runners. These are all going to be either 1, 2, or 3 because there were 3 races. Okay, I don't have the solutions listed here, but so some of these we already did, so we'll skip these. So the race associated with the first observation is race 1. The race associated with the second observation is race 2. The race associated with the fourth observation is race 1. So the fourth observation came from race 1. And the race associated with the sixth observation is race 3. All right, now let's use what we've learned in an example. And we're going to be talking about residuals, and we'll define what we mean by that. Okay, so just an extra bit of notation. And this is notation that we'll be using when we talk about factor models in regression. So let's suppose that B1 is the expected time from runner 1. B2 is the expected time from runner 2. So on and so forth. If you had more than 2 runners, B3 would be expected time for runner 3. In this data set, we just have 2 runners. And what we're going to do is we're going to define something called the residual. And here, the residual, I'm going to use the symbol E. And E sub I is the ith residual. And we'll define that as the ith observation minus its expected time. So the ith time minus its expected time is the residual. So this is the residual for observation I. And if we're going to write this out in terms of our notation, E1 is the first residual. This is going to be Y1 minus B1. So the Y1 is because it's the first observation. The B1 is because this came from runner 1. All right, do the next one. E2 is the second residual. This is Y2 minus B1. Again, this is because it's the second observation, and the expected time for the second observation is B1 because that came from the first runner. Likewise, E3 is Y3 minus B1, but E4 is going to be Y4 minus B2 because the fourth observation came from the second runner. Now what I want you to do on your own is to repeat this exercise, but we're going to use this double subscript notation. So what this EIJ means is it's the residual for runner I in race J, and I want you to write out each of these in terms of YIJ and BI. So BI is the expected time in a marathon for runner I. So I want you to do the same thing as we did up here but write it out in terms of Yij and Bi. So you can pause and do that, but might as well just finish up here because this is the last page. So this is just a sort of a brief overview of what the kind of mathematical notation we're going to be using. We're going to be using subscripts, double subscripts. We're going to be using summations, and we're going to be using indexing functions. And in this class, we're going to get somewhat complicated because these are the sort of models that people use. And so we'll write out things like this. Yi is a0 plus a sub ji plus b sub ki plus ab ji ki plus co times c0 times xi plus epsilon I. So this is going to seem a little bit overwhelming at first, but we're going to build up to things like this step by step. And if you were to just analyze what each of these are things that you can do. But this may seem a little bit overwhelming at first. So we're going to build up to it step by step, and we're going to figure out what this equation actually means in intuitive terms.